Hello everyone. Today I want to briefly explain Snell's law and total internal reflection and practice some questions. We need to start with the definition of refraction. So, refraction is the bending of a wave when it travels from one medium to another. So, if I draw this medium, for example, let's say I have this is my medium number 1, and this one is medium number 2. If I have a light traveling from medium 1 to medium 2, and this one is normal, this one is normal, and this one we know is incident ray. Because the speed of light is different in medium 1 and 2, so the light bends. If the medium 2 is a slow medium compared with medium 1, it means the speed of wave is slower here, something that happens, the light bends towards the normal. So something like this one, it comes here. So this is refracted ray, this one is refracted ray, and this one is angle of refraction. For example, theta r, and this one is angle of incident, or theta I. So theta r is smaller than theta I if medium 2 is a slow medium. Always the amount of refraction depends on the indices of refraction of two media. Okay, but what's the refraction index? The refraction index, just I write it here, refraction index. The refraction index defined as we showed by n, and is defined as c divided by v. That c is the speed of light in vacuum, and v is speed of light in the medium, or the medium that we want to study in the medium. Okay, and then n is refractive index of that medium, of the medium. Okay, so it's the definition of refraction index. Then something else that you need to know is Snell's law. So I go through definition and formula. So Snell's law is m1 sine theta 1 equal n2 sine theta 2. What does it mean? It means if I name this one medium 1, and then refraction index for medium 1 is m1, refraction index for medium 2 is n2. So it means m1 times sine theta 1, that is theta is this angle, equal n2 times sine theta 2, that is this angle. That we can write it like this way. So sine theta 1 to sine theta 2 actually is equal n2 to m1. On the other hand, we know n2 is equal to cv2 and m1 equals cv1. So I can write this one, n2 to m1 equal v1 to v2. And as we know, v equal f lambda, and f doesn't change because it depends on the source of light, so it's constant. So f of light in both medium are equal. So I can write f lambda 1 equal, and for V2 I can write f lambda 2 simplify to f. So I can get this relationship between n sine theta 2 and lambda, that we can use it in our calculation. The next thing that I like to discuss is the total internal reflection. The total internal reflection. So if the light travels from a slow medium to a fast medium, so in this case, if this one is a slow medium and this one is fast medium, when I'm saying a slow medium and fast medium, I mean the speed of light here is slower than this one. So if the light travels from a slow medium to a fast medium, what happens? As I explained, when it goes from slow medium to fast medium, something that happens actually, if I have this light, so if I draw the normal like this, so just my drawing is not good, and then if it is the angle of incident in this case, then refracted ray, because this medium is faster, actually is going away from the medium, so it becomes something like this. And if I name this one theta r, so this one is bigger than theta I because it goes from slow medium to fast medium. So as you can see, the refracted angle is greater than the incident angle. But if I increase the incident angle, then the refracted angle becomes bigger and bigger. And by the time that it gets to 90 degrees, so I make this one a little bit bigger. So as a result, my refracted angle, let's say it becomes a little bit bigger. And if I make it larger, we get to a point that actually refracted angle is 90 degrees. You know that when we want to measure the angle, it's the angle between refracted angle and normal, that this one is normal, that you see is 90 degrees. When the refracted angle is equal 90 degrees, then the incident angle is called the critical angle. So what I'm saying, when theta r is equal 90 degrees, then we name theta I as theta c, and we say critical angle. And if I use Snell's law again, we know m1 sine theta 1 equal n2 sine theta 2. So as a result, m1, if I want to find critical angle, so I put theta 1 as critical angle, theta c, it means it's equal n2, and your theta 2 should be equal 90. And you know sine 90 equal 1. So as a result, sine theta c equal m2 divided by m1. Okay, but why it's important? For the incident angle greater than critical angle, the total internal reflection will happen. What does it mean? It means after that, if theta I is larger than theta c, actually reflection of light start happening. So it means right now, if I say this angle is, if I say this angle, this big one is theta c, if I have a light with angle bigger than theta c, actually instead of refraction, I have reflection of light after that. So the light gets reflected. So and we name it the total internal reflection because the light can't go out, so it's reflected. And remember, because reflection is happening here, so we have the law of reflection. So it means this angle, this big angle that I just showed with purple, this angle, that is angle of incidence, is equal the angle of reflection, because right now it's reflection. So the law of reflection works here. Okay, let's go through some questions now. A light with the wavelength of 410 nanometer. So you know, this is our light, nanometer, and this is lambda. Travels from air to water. So to make it easy, just I draw it. The light travels from air to water. So it means air is my medium 1, water is my medium 2, and I have the wavelengths of light. Calculate its wavelengths in water. So I have wavelengths of light here, that is 410 nanometer, or I can say 410 times 10 to the power minus 9 meter, and I want to find lambda 2. As I explained, we have a lot of formula to use. The formula that we need to use, because we have our n, they're given to us, and we have one of the lambda, we want to find the others. The formula that we need to use is this one. So N2, that is our water, is 1.33. For air is 1. Lambda 1 is nanometer. I put in nanometer because it doesn't matter if I put this one in nanometer, I get lambda 2 also in nanometer. So it's okay, just I leave it this way. So as a result, lambda 2 equals 316 nanometer. How it was 315.8, just as rounded off to this. Okay. If the speed of light in air is 3 times 10 to the power of 8 meter per second, calculate its speed in water. Right now, again, we see we have our n, but we want a relationship between n and speed. So we know n2 to m1 equal v1 to v2. So 1.33, 1, speed of light in air 3, because it's medium 1 and medium 2 is v2. So v2 is equal 1.67 times 10 to the power 8 meter per second, or I can write in 1.7 times 10 to the power 8 meter per second. Okay. Next question. Calculate the critical angle for light traveling from water to air. So definitely we know whenever we talk about critical angle, the first medium, that is medium 1, that here is water, and medium 2, that is air. Whenever we talk about critical angle, definitely light needs to travel from slow medium to fast medium. Otherwise, we don't have any total internal reflection. It can't happen if the light goes through fast medium to a slow medium. Okay, so right now we see we have that light going through water to air, and then we have n for both of them. Something that we need to find just is critical angle, or theta c. So again, if we use Snell's law, sine theta 2. As we can see, we have m1, we have n2. We don't have theta 1 and theta 2, but we are looking for critical angle. So it means theta 1 actually is, we show it with theta c. And when you talk about critical angle, it means your theta 2 is equal 90. So and it's 1. So as a result, sine theta c is equal 1 over 1.3 3, and theta is equal 48.75 degrees. Thank you for watching.